Okay, we're going to do a little review today on chapter 10 and 11. And the way I'm using the review documents, and I've compiled them into a single document, so I don't have to reshare. And I've highlighted some ones that I think are representative of the topics that we've covered. And the way it's laid out, it's this was one of my earlier versions, and I haven't updated it. So I'm going to have to preface with some information here. This is chapter 10. And these are the easy ones because if I start renumbering as I go from easy to moderate to difficult, then the numbering system can get confusing. Okay, so before we get started, anybody have you run across any problems in the review document or anywhere else that are giving you trouble and we need to deal with it first? I want to do that before I start my spiel. Feel comfortable so far? Okay. So let's say we have these different molecules. And I'm just going to write the letters up here for each one of those. And we've got sodium sulfide, we've got hydrogen fluoride, right? It doesn't say it's aqueous, so we can't call it hydrofluoric acid. HF, ammonia, nitrogen, and water. And we're looking for the one with the lowest boiling point. So remember what's required to assess any of these physical properties. We need to have an idea. There she is. We need to have an idea of what's attracting the molecules. Are the forces strong? Are they moderate? Are they weak? In this case, we're looking for the weakest one, right? The one with the weakest forces. Remember? And the strongest intermolecular forces will be anybody? Dipole, particular hydrogen bonding. Hydrogen bonding will be the strongest intermolecular forces. That is, if we exclude ionic forces. We consider those intramolecular. But for covalent compounds, the strongest forces are going to be the dipole-dipoles. And the strongest of those are hydrogen bonding. So we can take a look at our choices here, and we find which one has available hydrogen bonding. Well, water and HF both have. So they would be candidates for the strongest or the highest boiling point. The lowest boiling point are the ones that don't have dipole possibilities. And then they're relegated to accessing only the London dispersion forces, right? So what we're looking for there is, if it's available, is completely non-polar compound, right? And compound is the right term for these because we don't have any noble gases in there. If we had noble gases, of course, they would be completely non-polar. So which one of these is definitely non-polar? Any ideas? No, nitrogen. Oh yeah, nitrogen would be this one right here. Well, the answer's up there, right? So I shouldn't be surprised if somebody gives me the right answer. I do that. I use this version with the key in it, so that as we work through the problems, maybe I've made an error in your answer key. So this is one way to find some of those errors. If we try to work them in class and say, wait a minute, uh-oh, that's wrong. And it has happened. Especially if I trust the creators of the key. The publishers, they have a tendency to get wrong answers. Sometimes bad questions too. Okay, number 3 I want to look at find one that's not fading on me. When a water molecule forms a hydrogen bond with another water molecule, which atoms are involved in the interaction? All right, we need to know something about the water molecules and how their dipoles are arranged. These bonds are polar toward the oxygen because it's more electronegative. So that means this end of the molecule is going to be the slightly positive end, and this is going to be the slightly negative end. So when they interact, it's purely electrostatic. Right? So the hydrogens, the positive end is going to be attracted to the negative end, and that's where we form the bond, the intermolecular bond. So which one of these statements is the most accurate? Well, you can go process of elimination. If we start with A, say hydrogen, a hydrogen from one molecule and a hydrogen from the other. Can't be. They would repel one another. B, a hydrogen from one molecule and oxygen from the other. Well, we found our answer. Right. If you have some wonky ones in there, this is test-taking technique for multiple choice. If you have ones that say one of the above, two of the above, none of the above, A, B, and C, or those kind of that depend upon the previous answers, then you might have to go through all of the, say, A, B, and C are unique answers, and then D and E are selections from those two. In order to eliminate D and E, you'd have to go through A, B, and C, all three of them, to be sure. But if you don't have that kind, like we have here, these are all 5 unique answers. And if you're in a hurry in a test and you go from A and you go to B, says that's the right answer, bam, move on. Right? Anybody taking standardized tests where they time you, right? And they have, I don't know what they use now, buzzers or bells or something. And you have to, you're in mid-stroke and you have to stop. Right? When you're in time constraints like that, you want to move quickly. So it pays to do 2 things. One, know the material thoroughly so that when you work your way down through these answers, you find the right one, you can put that down and go. If you're insecure, then you might have to go through several and use a logical approach to try to eliminate the wrong ones. That doesn't always work either. Okay, let's see. This one, only 4 is based upon one or all of these figures. Let me reduce the size so we can get them all on the same page. All right, so we're looking at number 4. Oops, didn't need to do that. Okay, so what is the question saying? Then we'll go back up to the pictures and see which one we're referencing. Which of the following statements are incorrect concerning drawing 3? Okay, so we can leave it like that. So we're looking at drawing 3. And we want to find the incorrect statement of these. Notice this one does have a wonky one at the bottom. 2 of the above statements are incorrect. So this says 2 above are wrong. So if we find one wrong one, that's okay. But we got to look at the others to be sure that we can eliminate E. Okay, A says electrostatic interactions exist between the molecules. Okay, what kind of molecules do we have? Might have to squint. That looks like hydrogen chloride. Right? So hydrogen chloride is going to be a polar molecule. If you look with the difference, hydrogen's up there at something like 2.2 or so. Chlorine's over here, and it's fairly close to fluorine, so it's going to have a much higher electronegativity, and I suspect it's going to be polar. So when they orient themselves, how do they do that? I mean, this is really a rehash what I've said at the very first statement. These interactions are electrostatic. You know, they're positive and negatives attract one another, and like charges repel. So yeah, that's a true statement. These interactions are going to be electrostatic. So A is true. That doesn't fit the bill. We're looking for the bad ones, the false ones. The molecules find the best compromise between attraction and repulsion. That's also true. We looked at that in terms of forming a bond, where the hydrogens approach one another and form the bond. That may have been in a last semester, wasn't it? When we were looking at covalent bonds. But you can also use that same logic when you've got polar molecules approaching one another. When they get close enough so that the negatives and the positive ends attract, if you get too close, then you start to get that, say this is the positive end, the negative end of the other molecule. You've got a positive end for this molecule, and if you get too close, you're starting to interact this positive with that positive, and you get repulsion. So there's a happy medium in between, an ideal distance. So that's why B is also true. C says these molecules exhibit ionic bonding. No, hydrogen chloride is a covalently bound molecule. We know that. So that one is false. And the interactions between them are definitely not ionic because you don't have complete transfer of electrons to get the ionic charge. Right? So we can say on two levels, both the intermolecular and the intramolecular, there's no ionic bonding involved whatsoever. So C is false. How about D? OCS exhibits this type of interaction. Okay, OCS is their idea of a molecule. So if we want to assess this completely, we would draw the Lewis dot structure. But I think just to answer this question, all we have to know is this is the correct order, some kind of bond between the two. And oxygen and sulfur are more electronegative than carbon, so we're going to get dipole bonds that way. But are they equal? If these dipoles are not equal, then we'll get an unbalanced distribution of electric charge. And oxygen is above sulfur, so it's more electronegative than sulfur. That means the resultant of these two should be in that direction. So we would get a slightly negative on this end, slightly positive on that end, and it would exhibit similar bonding characteristics, interactions to the the Roman numeral 3 molecule we're looking at. Okay. We didn't really have to draw the full diagram. If we had, we definitely have like that, probably like that. And then might even have to have a double bond on both sides. Probably so. This looks like it's analogous to carbon dioxide. But you don't have to know that to solve the problem. That's the good news. All right. Number 6. Like I've said before, during the discussion, if something just pops into your head, say, wait a minute, I need to talk about this, then stop me and we'll digress. Okay. Which best explains the following trend? Okay, what trend is that? Well, we've got, it looks like, the noble gases in order from the periodic table. Helium, argon, helium, neon, argon, krypton, xenon. And next to each one is its boiling point. I think I mentioned this in class. As you go down, we know that these are nonpolar atoms. Individual atoms have to be nonpolar if they're neutral. But the bigger the atom gets, which is what's happening here, we're adding orbital levels as we go down. And so it's getting bigger. And large size means that you've got more room to temporarily redistribute electron density. So that means that we know that dipoles are not involved here. So we're looking at London dispersion forces. So as you go down and the atom gets bigger, there's a greater chance, talking probabilities here, of electron density shifting out of place around that larger and larger and larger atom. So you should expect to have stronger, more persistent, on the microsecond scale, more persistent, unbalanced electric charge. And that would give you stronger attractions between the atoms. So that means the boiling point would go up as the London dispersion force strength increases. And that's the explanation for this one. And the best one to answer that is the London dispersion force is A. That explains it. You can't explain it with dipoles. You can't explain it with hydrogen bonding. And Le Chatelier's principle was thrown in there as just to confuse you, because it has absolutely nothing to do with the problem. Remember Le Chatelier? We haven't covered that yet, ever. Okay. Well, that's good. It's a mystery. So you can throw that one out just on principle. Okay. Number 7. Which of the following compounds has the lowest viscosity? So we want low viscosity out of these 5 possibilities. Okay. There again, viscosity is one of those things that is directly proportional to intermolecular attractions and intermolecular forces. What's the only one that's inversely proportional? Right. As the forces increase, what decreases? Remember, vapor pressure. You increase the strength holding molecules together in the liquid phase, then there are fewer of them that migrate into the vapor phase. So the vapor pressure is going to be lower as the strength increases. Okay, that's the only one that's inversely proportional. The rest of them are directly proportional. You increase the strength, you increase the magnitude of whatever we're discussing, in this case, viscosity. So if the attractive forces are stronger and stronger and stronger, the viscosity goes up. Okay, we're looking for the one that has the lowest viscosity. So we want, definitely want a nonpolar molecule, right? And the least polar of all that group in there is, again, nitrogen. This one. I think that's nice. Yeah. Okay. So we got hydrogen chloride, which is polar, water, which is polar. Carbon tetrachloride is nonpolar, but it's a larger molecule than nitrogen is. So you have the opportunity there for stronger London dispersion forces than nitrogen does. Okay. Plus you've got, well, carbon tetrachloride, you have, okay, let's go back to the slide that gave you a color referenced electron density. Remember that one where the reds colors were more electron density and the blues were less. Even though this one would be nonpolar because these polar bonds all cancel each other out. So overall, the molecule is nonpolar. But each one of those bonds gives you an increased electron density out here, right? So, and it can shift. And since it starts out with these polar bonds and you can get shift in a large molecule like that, the London dispersion forces are going to be stronger. Plus, well, there's a gradient between dipole and London dispersion, just like any other topic we've discussed. We can call it ionic, we can call it covalent, but there's always in between. Okay, same thing with London dispersions and dipoles. And this is one example. So you already start with an uneven distribution out here, even though it's uniform around the molecule. These things can shift, and they can give you increased London dispersion versus something like this, which is a smaller molecule and fairly uniform distribution of electrons around there. So the tie here between viscosities is going to be here and here. And the tiebreaker is the fact that this is smaller and it has non-polar bonds to begin with, whereas this one has polar bonds. So this one's going to have the lowest viscosity. Second lowest will be that. Okay. And then you can go to the dipoles and see which one has the strongest dipole. So the highest viscosity there would not be a gas. Right? Gases typically have very low viscosity. So even though hydrogen chloride is a, that's another point. This is a gas, and this is a liquid at room temperature. And liquids typically have higher viscosity. Right? So I was chasing the wrong horse around the barn. Just look at the phases. Gases are always lower viscosity than liquids. So you could solve that problem based upon the argument of gas versus liquid, right? How many liquids we got in there? We got grease, we've got water, we've got carbon tetrachloride. Throw those out. Now it's based upon phase. It's an argument between nitrogen gas and hydrogen chloride. And hydrogen chloride is definitely polar. So there, the tiebreaker is between those two gases. So either argument works. It's just, I think the phase difference is better because the viscosity is radically higher for liquids than it is for gases. So that's probably the last argument I gave you is probably the better one. But if we increase the temperature to where we could get carbon tetrachloride in the vapor phase, then I could go back and talk about that, my first assumptions. Okay, let's go to 8 now, before I step on my tongue again. I didn't get a chance to treat the board this morning. Our boards don't work as well as the ones in Greenbrier campus. I don't know why. Maybe they don't use them as much as we do. Number 8. When a nonpolar liquid displays a convex meniscus, which of the following explains its behavior? We got a nonpolar liquid, and it gives us a convex meniscus. So whatever's down here is immaterial for now. What are we saying here? There's a balance between the adhesive and cohesive forces. And actually, it's a competition. Which one wins? When the meniscus is convex, convex, the adhesive forces are stronger than the cohesive. Cohesive forces are stronger than the adhesive forces. The forces pulling that nonpolar liquid together are stronger than the forces between the nonpolar and the walls of the tube. Okay, and that makes sense, especially if the tube is glass, because glass has a polar surface. Right? It's silicon dioxide. You have those oxygens sticking out there. And if this is a nonpolar liquid, you're not going to get much interaction between the two. But if you have water and glass, they're both significantly polar, and you're going to get a very strong interaction there. Then the meniscus goes the other way. So which one of these fits that scenario? A says it has a low surface tension, therefore clings to the glass. If it clings to the glass, it's not going to cling to the glass because of surface tension. Low surface tension would be the other way around. This nonpolar liquid is showing you that it has very high surface tension because it's trying to form itself into a sphere. And the only thing preventing it is more of its neighbors below plus the gas. So A just doesn't ring true. B says the cohesive forces are stronger than the adhesive forces. That's the one I'd pick. All right. Which substance can be described as cations bonded together by mobile electrons? That was toward the end of the chapter. I think we discussed that. That model is characteristic of metals, right? The electron C model, where you have metals. Let's pick something interesting like gold. So you have these gold cations, and you got electrons all over the place. Let's see, 1, 2, 3, 4. Oops, I better put another one. Balance charges. So, which one talks about that? Well, we've got examples here. So, which one fits the electron C model would be whatever metal is there, right? And that looks like silver. Oh, that wasn't gold. That's silver. Sorry. Y'all should have caught me on that. Right? What's gold? You, yeah. I did have you memorizing that one, didn't I? Wasn't that one of the 60 odd symbols I had you memorized in the first semester? Did y'all have to memorize the whole periodic table? Oh, huh? In high school. Oh, okay. I just had my student memorize 60 of them. I picked them out, the ones that are most commonly used. Most of them up here in this range that contribute to compounding. Okay. Well, you got to step up. You probably know some of them there that I don't even remember. Yeah. Which of the following statements about steel is false? All right. It looks like we've got a one. E says, oh, okay. Yeah, all are true. All are true. So we have to go through there and find out which one is false. All right, if we find one that's false, then we can cross out E. So steel, it contains carbon atoms in the holes of its iron crystals. There's Madison. Better late than never. Oh, it has been a week. Okay. Okay, so that one is true. Right? That's what type of alloy is that? Right? Remember there are two types: substitutional alloy and interstitial alloy. Carbon in the holes, in the voids between iron atoms or crystals is an example of interstitial. So that's true, that statement. The presence of carbon-iron bonds in the alloy makes steel harder and stronger than pure iron. Yeah, there is bonding between the carbon and the iron atoms in that molecule. That keeps the crystals from sliding past one another. That makes it hard. So the more carbon you have in there, the harder the steel. Of course, the downside of that is what we get from solid nonmetals. Solid nonmetals may be strong, but they're brittle. So if you put too much carbon in there, you start to make your steel brittle. It can have a very sharp edge, but it's not very tough. So that's one of the reasons that the Japanese metal workers, when they came up with their blades, the most famous of those would be the katana. They incorporated two alloys of iron. They had soft steel in the center, and they had hard steel on the outside. And they modified the crystal structure also by, once they got the shape of the sword, then they dabbed the clay on it, on the thick side of the blade, so that it would cool down slower. And they left the edge open. So when they heated up to a certain temperature and then quenched it, the quenching would harden that edge very hard, but it would slowly cool the thicker part and leave it tough and flexible. And then they would sharpen it. And supposedly, you rarely have to touch a katana blade. It just keep it clean. Okay, so I digress again. B, yes, the added carbon and the bonding makes the steel harder. Pure iron is relatively soft and ductile because it lacks directional bonding. That's also true. I mean, we didn't go into detail in the lecture about that, but the omnidirectional bonding in pure metals makes them soft. They can slide past one another. You could even use the electron C model to justify that one, right? The electrons are out here, and the cations are, they easily push them past the electrons. And there's practical evidence too. I mean, if you have pure iron, like a piece of pure iron, you can dig into it with your fingernail. And you've seen movies where somebody is paid with these like westerns, paid with a gold piece. They'll take it and bite it, right? See if they can put a dent in it, and that tells them it's gold. Okay, so let's see. That was C, wasn't it? Yeah. How about D? The amount of carbon directly affects the properties of steel. Well, yeah, it does. That's kind of another way of saying B. So they're all true. Okay. Number 11. Looks like we're getting into semiconductors here. Which of the following statements is true about P-type silicon? P-type silicon. We have pure silicon, and we're going to dope it with something to make a P-type semiconductor. So we have D and E say either all are true or none are true. So we're really looking at A, B, or C. A says it's produced by doping silicon with phosphorus or arsenic. Now, what do we need to give a P-type? We need to be deficient in at least one electron when we dope it. Okay. So we need something that's, if we go to the right of silicon on the periodic table, you're adding electrons. So we need to go to the left of silicon. So what would be left of silicon? Boron, aluminum, gallium would be good candidates. Is that true? Phosphorus and arsenic are to the right. That would be an N-type semiconductor. So this one's false. Protons are the mobile charge carriers. Does that make any sense? No. If you move a proton from an atom, before you can replace it with another proton, you've created a different element. So protons don't carry the charge. They don't move. Only the electrons move. Right? So B is also false. Just simply based on first principles. C says it does not conduct electricity as well as pure silicon. That's false. The whole point of doping silicon is so that we can make it more conductive. We want to control the conductivity. So we dope it at a certain level of the other elements to control that conductivity, because what are we trying to create in a semiconductor? Gates, current gates. And when we put a P and an N type together, we form a gate. And if we apply a biased charge to that, we can either exclude movement of current through it or promote movement of current through it. That control gives you in a computer chip, a bit. It either will move or it won't move, zeros or ones. So all of them are false. It's this one. Okay. All right. Let's try 14, see what we come up with here. I think we're still in the easy groups. A solid crystal of sodium chloride is sodium chloride solid. What are we looking at with a sodium chloride solid crystal? We're looking at a cube. We know that because we just spilled some salt on the tabletop and looked at it with a magnifying glass. And we saw cubes. And we've got an array of sodium and chloride ions. Well, let's see if I'm consistent with our previous drawings. Chloride would, well, actually, sodium's not going to be at the corners here. Chloride's the bigger one, so it's going to be here. Pretty sure. And then we're going to have sodiums in between. Maybe we need to have the same number of sodiums here as we do chlorine. So there are 8 there, and we've only got 6 sides, so I'm not sure how that goes. But what we've got is an array of sodium cations and chloride anions. And if it's a solid, those ions are locked in place. They cannot move. So they don't conduct electricity, definitely. And since they can't move, they don't conduct heat very well either. So, and since it's an ionic solid, we can say we expect it to have a high melting point. Right? So if we look at our choices, A through E, the first one is soft versus hard. Right? It should be hard. Right? Should be hard. So we're down to B and D, our possibilities. We can throw the rest out. The next one for B and D is high melting point, right? So both of them are hard, and both of them have high melting points. So let's see, what's next? B and D. B says good electrical conductor. D says poor electrical conductor. That's the one. Poor current. That's the physics. A variable for current is I. So D is your best answer. Fits all the conditions correctly. 15, I think. Saw 15 highlighted. Which of the following has the highest melting temperature? Right? I would look at the selections and say, which ones of these, if any, are ionic? Okay. Water's covalent, carbon dioxide's covalent, S8 is an allotrope of sulfur. So they're all covalently bound there. P4 is an allotrope of phosphorus. Magnesium fluoride is an ionic compound. It will have an extremely high melting point. Right? For 2 reasons. One is magnesium has a 2+ charge. And the fluorines even though they have single charge, are very small. Well, magnesium's small too, right? Because we took electrons away from it. So they're probably pretty close to the same size, but you can get them very close together. Remember the two things that determine strength of attraction, the size of the charge, and this is for ionic compounds, the size of the charge and the closest of the centers of charge. So you get them close together with high charge and you got a very strong bond. And that means high melting point. $16. How are we doing on time? Which of these statements is false? Okay. Diamond is a covalent crystal. Yeah. Right. In fact, if there are no flaws, it's a single molecule of covalently bound, tetrahedrally arranged, covalently bound carbon atoms. Well, that was true. The size, B, is the size of the unit cell of lithium, and cesium is the same. All right. If you're putting lithium into a unit cell and cesium, and notice that lithium and cesium are both alkali metals. So they're probably going to have the same type of unit cell. I'm trying to think of which one they said. I believe it was the simple cubic was the alkali metals. So let's just assume that for the moment. If you draw the simple cube and you put something at the corners, lithium, say, for one, and cesium for the other one, and these guys have to touch, right? They're going to touch. Cesium is a bigger atom than lithium. So it needs more space. It may be a cube, but it's going to be a lot bigger cube, right? Okay, so the size of the unit cells for lithium and cesium are not the same, simply because of their atomic size. None of the statements is false is E. We found the false one right here. So C and D should be true. Molecular crystals usually have low melting points. Yes, that's true. Molecular crystals, like, I don't know, what's a good molecular crystal? Table sugar? Yeah, table sugar. It has a relatively low melting point. I mean, you can put it in a spoon over a candle and watch it melt. And then if you like tilt it to the side a little bit and let the flame hit it, it'll burn. Burning sugar. I bet that smells good. Well, it does on marshmallows. Now, marshmallows are, marshmallows are primarily sugar, aren't they? Yeah. With a little gelatin to hold them together. And D says metallic crystals are usually good electrical conductors. Wait a minute. Metallic crystals. Yes. Yeah, metallic crystals are. Why? Because those electrons are free to move. Yeah. Yeah. So D is true. That means the only false one is B. All right. 17. How would you expect the melting point of carbon tetrachloride to compare to that of sodium chloride? Well, first of all, we're comparing an ionic compound with a nonpolar covalent compound. So the melting point for carbon tetrachloride should be a lot lower. But the statements look like they're saying this is why. It may be lower, but why? So if we say A, it should be lower, that's true. B, similar, C, higher, D, higher. Not possible to say anything. Well, I think we can say a whole lot about it. So based upon that, the only one that says lower is A. But let's see if that's true. Because sodium chloride forms an extended ionic crystal lattice, whereas carbon tetrachloride is covalently bonded small molecule. That's part of the way there, right? But since it's the only one that says lower, we have to go with it. That's why A is probably the best answer. And that's another rule to go by. You guys have heard me say this before. When you're taking a multiple choice test, and you think that all the answers are not exactly what you think they should be, pick the best answer. Especially if you're taking a standardized exam, like the SAT or something like that, because those are going to be machine graded, most of them. Well, except for the essays, somebody has to read those. But the math part of the test, and all the multiple choices, they're going to be machine graded, and they don't care who you are. You could be another machine taking the test, and they wouldn't care. Okay, 19. At normal atmospheric pressure and temperature at 0 degrees C, normal atmospheric pressure. So pressure is equal to 1 atmosphere. Temperature is equal to 0 degrees C. That looks like standard temperature and pressure for all gases. If we've got gas problems, that's the standard. Which phases of water can exist? If we're at 1 atmosphere pressure and 0 degrees, if you look at the phase diagram for pressure versus temperature, we go up to here and then we go up, oops, this is water, sorry. Then we go here and then we go maybe out like that. So that's the triple point at which you're going to have all three phases together. We know that doesn't happen at 1 atmosphere and 0 degrees. 1 atmosphere pressure is probably going to be in this neighborhood, 1 atmosphere. And temperature of 0 degrees is going to be somewhere out here. So we're actually looking at, well, actually, it's not in this region. It's probably on the line. I bet it's right here. That's equal. You're going to have both solid and liquid together, right? We know that from practical experience. If you have distilled water and ice made from distilled water, and they're both there in the beaker at 1 atmosphere pressure, you're going to have 0 degrees, and it's going to stay there until all the ice melts. So the answer to that one is you're going to have ice and water together. We're actually on the phase line for, let's see, solid and liquid. Remember what this point is out here? Critical point, right? So at any temperature past that and pressure above that, you have a critical, supercritical fluid. Number 20. Which of the following processes must exist in equilibrium with the evaporation process when a measurement of vapor pressure is made? Which of the following processes? Okay, we're talking about if we're measuring vapor pressure, say in Erlenmeyer flask, and we've got a stopper up there. We have to have a liquid here, and we have to have vapor there. So the process is evaporation is given to us. What's in equilibrium with evaporation? Condensation. So E is the answer to that one. How do we change the vapor pressure? Three ways I can think of. Change the temperature, right? You can increase the vapor pressure. Change the material, change the liquid, get a different vapor pressure. Or we can dissolve something in it. A non-volatile solid will do. Dissolve that in there, you'll decrease the vapor pressure. You're given the following boiling point data. Which one of the liquids would you expect to have the highest vapor pressure at room temperature? Okay, so now what we're doing is we're comparing two different, two properties, proper word, two properties, and they're linked by intermolecular forces. So if we're saying that the vapor pressures are changing, is the vapor pressure, let's see, highest vapor pressure at room temperature. So what we're looking for is an indicator of what are the intermolecular forces, right? And the boiling points are given. The higher boiling point is going to have the stronger intermolecular forces, right? Which means the lowest vapor pressure. So if we're looking for the highest vapor pressure, we want the lowest boiling point. And that would be diethyl ether, D, 34.5 degrees. That will have the highest vapor pressure at any given temperature compared to the others. 22. Which one of the following decreases as the strength of the attractive forces increases? Well, we just talked about that. That's vapor pressure. It's inversely proportional. You just have to memorize that one, I guess. 23. Hurry. In which of the following processes will energy be evolved as heat? Okay. So let's say we have solid, liquid, gas. And if we're going from a solid to gas, what's that called? Sublimation. Is that what you said? Oh. Sublimation. All right. Is that an endothermic or an exothermic process? Right. The material, the solid, is the system. So do we have to put energy into the system or remove it to go from solid to gas? We have to put energy in. This is endothermic. So delta H is going to be positive. The other direction would obviously be delta H negative, which would be deposition. I used to be an amateur astronomer. I never got around to making my own mirror, but I knew the process. The grinding is very tedious and time consuming. But once you get your mirror right shape, the perfect parabola, then you have to send it to a company that will silver the surface. We say silver the surface, but usually it's aluminum. And what they would do is they'd put it in a vacuum chamber, and up here somewhere, they'd put a chunk of pure aluminum, and they'd heat it up. And under vacuum, it would sublime from solid to gas. And those aluminum atoms would fill the chamber, and they drift, and they would settle on the surface of that mirror. And after you had enough of them on there, that gives you the reflective surface, then they stop the heating and crack the vacuum and pull it out and check the surface. Well, what's happening first is the sublimation of the aluminum, and then when it deposits on your mirror, that's deposition. Okay. They might even cool the mirror somewhat to accelerate the process. Okay, so if we go from gas to liquid, or from liquid to gas, let's say inside we're going this direction, outside we're going that direction. Liquid to gas would be vaporization. Right? Then we would have to add. That's an endothermic process. And going this direction is gas to liquid is condensation. Condensation, which gives up energy as we go from gas to liquid, because the gas molecules have a whole lot more kinetic energy than the liquid does, and we have to conserve energy. So if we're going from gas to liquid, we've got to get rid of that energy somehow, and this is an exothermic process. Okay? And then the last one, solid to liquid. Let's see, inside we're going this direction. So liquid to solid is freezing. And as it freezes, it gives up energy, exothermic. Excuse me, that's it, exothermic. And then this way is melting. And that's going to be endothermic. There we go. So to answer the question, in which process will energy be evolved as heat? In other words, exothermic. This is an exothermic process. Deposition, is it there? Nope. This one, condensation. It's not there. Freezing. Freezing. Oh, okay. We got another one. Crystallization. Okay, this is not strictly speaking a physical process. What do we mean by crystallization? Usually we mean an ionic compound where you've got sodium, for our example, sodium ions and chloride ions, say in aqueous solution. And they're coming together as a solid. So you can do that two different ways. You can, actually the best way, the quickest way is to cool the solution. So the solubility goes down and then they start to drop out of solution. So when you cool the solution, what's happening? You're extracting energy. It's exothermic process. So crystallization would be the best answer there. It's an exothermic process because this is more stable than that. This is at lower energy than that, and the energy's got to go somewhere. So it evolves as heat, exothermic. I didn't need to tell you about all that, I guess. But it's there for your amusement. All right, 25. Choose the correct statement about the diagram below. Okay, what we've got here is a phase change diagram with temperature on the x-axis, pressure on the y-axis, and we see the phase lines. The phase line between solid and gas is down the lower left, and the phase line between liquid and solid is the positive slope one in the middle, and then the one between liquid and gas is the third one on the far right. And that other line is just to show you where one atmosphere is located. Okay, that sets the stage. All right, which is the correct statement out of these? Do we have any wonky ones? None of the above statements is correct. All right, and the rest we have to look at. So A says the diagram is qualitatively correct for water. Is that true? What's the slope, the direction of slope between solid and liquid? For this one, it's positive, which is for most solids, that's true. But for water, it's not. Right? It should be a negative slope. So that's false. That does not represent water. The diagram shows that the melting point of the solid increases with increasing pressure. Okay. The melting point is going to be on that line between solid and liquid. Okay. Right up here. So as we increase the pressure, what happens to the melting point? It's a positive slope. The melting point increases. Melting point of the solid increases with increasing pressure. That's true. It's a positive slope. So none are true. Right? That means we can throw this one out. So we really found our answer. If we look at the other two just for curiosity, the diagram shows the triple point about 1 atmosphere pressure. Nope, it's a lot lower than that. A lot lower than 1 atmosphere pressure for that triple point, where all three of those lines come together. And then the diagram could represent the phase diagram of CO2. Well, what would happen on that line if we, at 1 atmosphere, if you take dry ice and set it on the tabletop, what's it going to do? Yeah, it'll vibrate because it's subliming, right? It's producing those gas bubbles underneath it, and it makes it do this. That's true. Okay. But what I was getting at was, could this be the phase diagram for carbon dioxide? No, because if it were at 1 atmosphere, as the temperature increased, you go to liquid first and then to gas. So that line, that 1 atmosphere line for carbon dioxide, should be much lower, down on the lower end of the solid, where it can go across at increasing temperature and go straight to gas. Right. That would be a carbon dioxide, closer to a carbon dioxide phase diagram. So D is false also. Oh, got another one, 26. Let's see, is that A through E also? Yeah. All right. 26. What are we looking for? Below is the phase diagram for a compound Q. You wish to purify a sample. I might have to draw this one. Purify a sample Q that was collected at pressure 1 atmosphere and temperature 100. Okay, so let me try to rough this one out. Temperature, pressure, and we've got that. This is 1.5, this is 1, this is 0.5 atmospheres. Okay. Temperature goes from, in Kelvin, goes 1, 2, 3, 4. Just goes up to 3. All right, let me redraw that. Spread it out a little bit. This goes back to your first lab exercise, graphic techniques. So if I put 3 out here, that, then 2 would be about here and 1 would be about there. There we go. And that's Kelvin. Okay, now draw the diagram. So where is the triple point? It looks like the triple point is just shy of 200. Okay. And just above 0.5. So it's right about here. Triple point. And then we get that, get like this, that. And then this one goes down to there. Okay. So if we've you want to purify a sample of Q that was collected at 1 atmosphere pressure and 100 K. So at 1 atmosphere pressure and 100 K, that's where we collected Q originally. Right? But we want to be sure it's not contaminated. So we want to purify it by a process called sublimation. In other words, we're hoping that any impurities in there will not sublime at the conditions we choose. We have to choose the conditions so that we can sublime it. We need to go from solid to gas. So what do we have to do? Well, we should decrease the pressure and then increase the temperature, and that will sublime it. That's kind of like freeze drying. You know what a freeze dryer does? You freeze your sample, put it in this chamber, pump out all the air, and then add a little bit of heat to it, and it'll sublime the water. I used to do that day in and day out, usually with plant samples. Shrimp boats would come in, and they take the shrimp and they cook them and peel them by machine, and rinse them, and they had this contaminated water that they had to get rid of, right? And they knew that down the road, EPA was going to say, you can't dump that in the canal. So they called us up at LSU and said, help, what do we do with this wastewater? Well, the wastewater was it was food grade, right? It was clean. So we took that and samples in big carboys, and we put it in a freeze dryer and dried it down. We freeze dry it because that would preserve any of the components without degradation from heat. If you boil it, you're going to change things. So we freeze dried it, and then we took those samples and said, what can we do with them? So we need to cool it down and then increase the temperature. So which one of them fits that? Increase the pressure? No, don't. That's A. Increase the pressure? No. C says increase the temperature to 300, keeping the pressure. If we do that, we're going into liquid, so that won't do it. Sometimes it helps to draw pictures. Lower the pressure to 0.5 atmospheres. Okay, yeah. You go down here like this. And then what? And then increase temperature to 200. Yep, that'll do it. So this one is true. Increase the temperature to 300. That'll take you through liquid, so we know this one's false. And then E, was it wonky? Abandon the attempt to sublime Q. We got 5 choices, and you can't think of anything else to put in there that's reasonable. You just make something up, right? And if the student's not paying attention, they'll pick that bad one. Okay. I'm giving away instructor secrets. Anybody planning on being an instructor in sometime in the future? I sort of had an inkling early on. It's just that I took a couple of education courses for my bachelor's degree. And I said, this is going to help me in the classroom. They were totally worthless courses. So at that, plus once I got my degree, I said, wait a minute, what are they paying teachers with a bachelor's degree? I can't live on that. So I went to graduate school. 29. Given the phase diagram below, which of the following statements, A through D, is false? Okay, that diagram below, you know, it looks like it might be water, right? Simply because of that phase line between solid and liquid is negative slope. That doesn't guarantee it, but it's a pretty good guess. So we were looking for the false one. The solid has a higher density than the liquid. Okay, how do we know that? The solid had, okay. Here's where you have to really make a big leap. If we assume that that phase change is a negative slope, and we say that it's water, we know that water has a lower density solid than the liquid. So A is true based upon that logic. And the others should be false. B, at some constant temperature, the gaseous substance can be compressed into a liquid and then into a solid and then into a liquid. Oh, we're looking for false, excuse me. how to read my own question. The solid has a higher density than the liquid. Oh, that's false. Solid has a lower density than the liquid, if we're assuming this is a water phase diagram. Yeah. All right, so A is the false one, and B, C, and D should be true. All right. I'm taking too much time. Oh, we're finally down to moderates, and numbering is restarted. Okay, so we got to go moderate now. I don't want to eat up too much of your lab time, but it looks like I've only got an hour left to get through chapter 11. Number 1. Maybe I'd better stick to the script. Which of the following is correct order of boiling points? All right. So now, instead of just saying which one's the lowest and which one's the highest, we want to put them in order. So we've got potassium nitrate, which is an ionic compound. We've got methanol, which is a hydrogen-bonded organic covalent compound. We've got C2H6, which is ethane, which is nonpolar. It's like this, and then hydrogen's out like that. And then neon. Okay, so we put them in order boiling points. And if we look at the answers, the lowest boiling point is on the left, the highest is on the right. So when I have to put things in order like this, I try to find the one that's farthest to the left and one farthest to the right, and then I work my way in with the others. So the one with the lowest boiling point would be the noble gas. So neon is less than everybody else. What's the highest one? The ionic compound. Now we need a tiebreaker between these two. This one is hydrogen bonded, and this one is perfectly nonpolar. It only has van der Waals. So it should be like that. One thing we also notice is this is a hydrocarbon, hydrogen and carbon. That's what we call it that. There's a sequence of hydrocarbons starting with methane and going through, this is propane, and this is butane, and just keeps going, gets bigger and bigger and bigger. We notice that the boiling point, melting points increase as you get bigger and bigger. That's because with larger molecules, you have two things going on. One is van der Waals forces are more prominent, because with bigger molecules, just like with bigger atoms, you have the probability of redistributing the electron density more greatly removed for larger molecules. Plus, as you get bigger and bigger, you have the possibility to align molecules and get more interaction between the molecules. And even the really large ones, you can get entanglement. So as you get in this homologous series of, we also call them alkanes, and that's a organic chemistry name. As we increase the length, we increase the boiling point and melting point for those reasons. So that's why, even though this one's nonpolar, it has a higher melting point than this one. Or is it boiling point? Boiling point. Okay, number 4. We're going to get some calculations here, it looks like. Might have to look up a formula or two. 4. Assume 12,500 joules of energy is added to 2 moles of water. So what are we given? The beginning heat, let's see. Let's say Q. Right? Q was our shorthand for heat, right? Thermochemistry. So we have 12,500 joules to play with. And we've got 2 moles of water. And so we've got 2 moles of water, which is equivalent to what? Well, 1 mole is 18.02. So roughly 36 grams of water. Okay. As at 0 degrees. So our starting temperature is 0 degrees C. That's what we're given. We're also given the specific heat of liquid water and the molar heat of vaporization at 40.6 kilojoules per mole. So we want to know what do we have when we finish using all of our heat. We've added all that heat to the water, and it goes from 0 degrees, which is a solid, at the melting point, up to wherever we are in that phase diagram. What do we have there? Do we have ice? Do we have ice and water? Do we have only water? Do we have water and water vapor? Okay. So this is the one we're looking at. This is as we add heat. Temperature. Yeah, temperature. So at 0 degrees, that's where we start. Right? And we're going from actually, we're not starting at 0. We're at something less than 0. Let's just pick a number, say minus 20. And at 0, that's where we're located. So we're not in this part of the diagram. We're up here at 0. And that's where the temperature is stable. And you have solid and liquid together. Down here, you only have solid. So if we're at 0 degrees, we're starting with solid, but now we're going to melt it. Right? So we're staying here at that temperature. So which expression do we need? Heat of fusion, kilojoules per mole. The heat of fusion tells us that the heat that's required for fusion or melting, right? They're reverse processes, is this constant value, 6.02 kilojoules per mole times how many moles of water do we have? Times 2 moles. So we're using up this many kilojoules, or 12.040 kilojoules, which is 12,040 joules. Okay, so let's put that over here. Starting with that many joules, and we've used up 12,040, right? Yeah. So what do we have left over? 460 joules. Okay. So when we get to this point where we've melted all the water and we're starting to go into the liquid heating phase, now we're talking about this equation. Let's see. Oops, did I use a K here? No, specific heat times mass times change in temperature. Okay. So we're given the specific heat, 4.18 joules per gram degree. Let's put it over here. This is the amount of heat that actually, well, let's leave it that way for now. 4.18 joules per gram degree C times mass, 36 grams, times change in temperature. All right. What's going to be our unknown? Well, if we have we know how much heat we have to work with. So let's make this one known, 460 joules, and our change in temperature will be our unknown. Okay, so all we have to do now is solve for a change in temperature. So that's 460 divided by 4.18, right? Bring it on this side. This is joules. 460 divided by 4.18 and divided by 36. So the change in temperature, here, let's put it over here. Change in temperature on this line equals 3.1 degrees. If we're starting at 0 and we go up only 3.1 degrees, we're still liquid, aren't we? Right? Because when we get to this point, that's 100 degrees. Right? That's liquid and vapor. Right? So we're still pure liquid, nothing else. So that's only, let's see, only water, C. Okay. When you first look at a problem like that, you're probably saying, what did I get myself into? But if you break it down and pull the information out of the problem, right? What have I said to this class before? What are word problems good for? Confusion. Word problems are written to confuse. So what they're testing is, do you know what to do with the information that you're given to answer the question? So they make it as confusing as possible. Sometimes they give you information that you don't need. Sometimes they don't give you enough information. And you have to go out and look for it, like go to the periodic table, usually, or remember the formulas. Well, in my case, look them up in the useful information. Okay. So everybody loves word problems, I know. And we got some difficult ones here. Okay. Number 1. So a crystal was analyzed with X-rays having 2.33 angstrom wavelength. 2.33, and the symbol for that is A with a 0 over it. Now, we haven't talked about angstroms, I don't think. Angstrom, 1 angstrom is equal to 10 to the minus 10th meters. So nanometer is 10 to the minus 9th. And what's the next one? Nanometer, picometer is 10 to the minus 12th. So this is in between those two. And it was commonly used for years, and may still be used in some arenas. But that's what we're given. The angle of the first order diffraction, n equals 1, was 19.2 degrees. Theta for first order is 19.2 degrees. Okay. What's the angle for the second order? So we're looking for the second order angle. Okay. What do we need to answer this question? No guesses? The Bragg equation. So that's one that you don't have to memorize, but you have to recognize it when you see it. So look at useful information, and I'm checking to be sure it's here. Let's see, Bragg, where's Bragg? There it is. Oh, I actually do label it Bragg equation. N lambda 2d sine theta. Okay. So we're going to do this at 2 different ends. The first end is going to allow us, by putting in the wavelength, and by the way, if you use the same unit of measure for the wavelength, maybe that does have to be converted to meters. Difficult number one. Let's see. Look at my handwritten explanation. Where is it? Yeah, here it is. Difficult number one. No, we don't. Why don't we have to change that to SI units? Oh, because if we use angstroms here, we're going to get angstroms there. Angstrom is a unit of measure, right? So whatever unit you use here is the same unit you get for the distance between the layers. We could change it to meters, right? And this would come out in meters, but we don't have to because we've got that one on both sides of the equation. They cancel each other out. Okay, I'm satisfied. So there are two approaches to this one. You can do it in two steps. Right? You can put in what you know here. Right? That would be 1, and then 2.33 angstroms, and then sine theta, 19.2 degrees, and find out what the D is. And then you could go to the second one and say, all right, we changed this to 2, and we got the same lambda, and we got the same distance between them. Put that in, and then solve for the theta. Or you can combine them into one equation and solve it once like that. It's usually easier for beginning students to do the two-step version. Makes more sense. Unless you're just a whiz at algebra, and then we can combine equations. But I'm assuming that nobody wants to do that. So the first one would be, n would be 1, right? And lambda would be 2.33 for, I'm going to leave the units out to save space. And D is our unknown, and then sine 19.2 degrees. And then we solve for D. Okay. So let's see, 2.33, and we're going to divide by 2. Bring the 2 over here. And then sine 19.2, and then bring it over here and divide. Okay. 19.2, and I'm going to take the sine of that if I can find my, here it is, and then divide that in. And D is 3.548. Okay. So now we can go to the second one. N in this case is going to be 2. Lambda's the same. And then we have 2 times 3.54 angstroms. And sine theta is our unknown. So we'll take 4.66 for this one. Divide by 2. Well, divide by 2, we're back to where we were. And then also divide by 3.54. And that gives us 0.658 equals sine theta. Now, how do you get theta from that? Has anybody had trigonometry in here? Okay. So you want the arc sine of this value to give you theta. It's like trigonometry's inverse. So where is it on your calculator? Well, if you find sine and you have a shift key that goes up to something above it, it's usually a sine, or it might say arc S or something like that. But that's where it's going to be located. So I need to put in that value, which is already in there, and then I just shift up to a sine, and that gives me theta is 41.2 or 41.1. Rounding error. Again, the best answer, 41.1 degrees. Okay, any questions? No. Bewilderment? Like I said before, this is where you learn chemistry, solving problems. Okay. Number two, chromium metal crystallizes as a body-centered cubic lattice. Chromium, solid, a body-centered cubic lattice. So we've got chromium, 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 chromium. Another chromium in the center. That's a body-centered cubic. If the radius of chromium is 1.25 angstroms, 1.25 okay, is equal to R. What's the density of chromium in grams per cubic centimeter? So we're looking for density, and we need mass per unit volume. Okay. So let's get the volume first. What's the volume of that cube? Well, we've got the radius of chromium. If we go to useful information, we should have, here it is, BCC edge. Body-centered cubic edge is 4R divided by square root of 3. So the edge here is A. And A is equal to 4R divided by the square root of 3, which is 4 times 1.25 angstrom over square root of 3. So we'll find that edge in angstroms. But notice we're looking for grams per cubic centimeter. So that's not the end of the story. That edge, why don't we go ahead and cube it, right? To get the volume. Just cube that, and cube that. And we can get the volume. Okay, 1.25 times 4 divided by square root of 3. And then cube it. I got 2.887, and then I'm going to cube that. So in my calculator, I have to put a 3 in and go to the power. Some of you have cube keys on your calculator, some of you don't. So that's 24.056 cubic angstroms. Now we need cubic centimeters. So here we go. We need to dimensional analysis. So if we've got 25.056 cubic angstroms, we need to convert angstroms to centimeter. We may not know that. So, well, actually, I can figure it out, but it may not be obvious to you. So let's do it in 2 steps. Convert to meters first. How about that? We know that 1 angstrom is 10 to the minus 10th meters. Then we can cancel the meters with centimeters. 10 squared centimeters is 1 meter. Here's the problem. That's cubic angstroms. So the solution to that is that. Okay. Did I lose anybody? No? Okay. So now, number crunching. So let's see. 10 to the minus 10. 1 exponent. And then 100. Oops. Got to go back. Do 4.056. I need to do 10, 1 times 10 to the minus 10 and cube that. Yeah. times 24.056. Okay. And then I want this one, which would be what? 10 to the 6th. 10 to the 6th, right? 2 cubed. So it'd be 1 exponent 6. This gives me cubic centimeters. 2.406 times 10 to the minus 23 cubic centimeters. Okay, we got the volume now. Now we need the mass. So what are we looking at here? The mass in that cube is how many chromium atoms are there in that cube? Well, there's one here that belongs to that cube and nobody else. But these guys belong to 8 others. So those 8 chromiums add up to another 1. So we have 2 atoms of chromium. Right? So 2 atoms of chromium we want to convert to mass. And the only way we can convert to mass for atoms is molar mass, which means we need to know the number of moles that represents. 6.022 times 10 to the 23rd atoms per mole. We'll get rid of the atoms. Now we need to bring it down here. Now we need to get rid of moles and leave us with grams. So that's chromium. So we go to our periodic table. 51, rounded off 2 places, 52.00. There we go. So now I can say 2 divided by 6.022, 10 to the 20, negative 10 to the 23rd, oh, positive 10. There we go. Divided, and then times 52. So I get 1.727 times 10 to the minus 22 grams is in that volume of cube. 1.727 times 10 to the minus 22 grams per 2.406 times 10 to the minus 23 cubic centimeters. So let's see if I've still got those in my, yep, just need to flip them and then divide. And I get 7.18 grams per cubic centimeter. That's B. Okay. I assume since everybody's quiet, then you got your right on target. Check my camera lately. It's still working. Good. All right. We're finally at chapter 11, and I've got 35 minutes left. I think I'm going to bleed over a little bit into lab time. And then we'll talk about, I'll give you the handouts for the lab. So we're up to chapter 11. And yep, this is the easy. Okay, number 1. In a 0.1 molar solution of sodium chloride, 0.1 molar solution of sodium chloride, and it's probably aqueous. Which one of the following will be closest to 0.1? All right, if you're in a hurry, then a little logic will help you here. This is molarity, which is moles per liter of solution. Okay? If we were to say molality, what are the measurements there? Moles per kilogram of solvent. Okay? If this is aqueous solution and it's dilute like that, then the density is probably pretty close to 1, which means 1 liter of solution is about 1 kilogram of solvent. So this should be closest to molal sodium chloride. Now, I think in the worked problems, I go ahead and calculate all 4 possibilities just to prove that I'm right. But this is the closest one. Molality is very close to molarity if they're aqueous solutions. So that would be D. The molality is very close. They're not all about 0.1. Mass percent is going to be radically different. Mass fraction, which is mass percent divided by 100. And a mole fraction is definitely going to be off because the molar mass of sodium chloride is a lot bigger than water. Okay, let's go to 2. All right, which of the following concentration measures will change in value as the temperature of a solution changes? I would look for any one of them that includes volume. If volume is included, it's definitely going to change with temperature. So mass percent, no, that's just a ratio of 2 masses, no change there. Mole fraction, that's numbers. Numbers are not going to change with temperature. Molality, it's ratio to mass, so it's not going to change. Molarity, it's ratio to volume. That's the one that will change. So D will change with change in temperature. Now, as a practical matter, if you prepare a solution in the lab at 25 degrees and we hit a cold snap and the temperature drops to 20 degrees in the lab, the difference in the 2 molarities is going to be negligible. Right? The only time it becomes a problem is when you're working with very, very accurate numbers, and you have to be exact. Now, it's a good practice, to be as meticulous about your preparations as possible. But as a practical matter, it won't have an influence. Right. So the last one, D, is the correct one. That will change with temperature. Now, if you prepare a solution that is extremely exothermic, right, that generates a lot of heat, when the temperature goes up to 80 or 85 degrees, when you dilute it, then if you set it on your bench on the mark of your volumetric flask, and you set it on the bench and let it cool down to room temperature, you'll see that volume drop by a significant amount. So in those cases, you'll want to add a little more water when it reaches room temperature and remix it. Now, if it's extremely endothermic, it gets colder, then if you dilute it to the mark at that cold temperature, when it warms up to room temperature, you're going to be above the mark and you're screwed because you can't. The only way you can do it is reduce the volume, right? I have done that in desperate situations. If you have a supply of nitrogen gas piped into your lab, you can just set the gas blowing in your the top of your solution, and it'll gradually decrease it where you can blow the line, and then you can bring it up to volume and mix it and go on your merry way. But it takes a while. Okay, number 3. Which of the following chemical or physical changes is an endothermic process? We have to put heat into it to make it happen. Evaporation of water, that's a good one. You got to add heat to change from a liquid to a gas. Combustion of gasoline, that's definitely exothermic. Right? Otherwise, we couldn't run our cars. The mixing of sulfuric acid and water, that's why they say, as a general rule, do as you oughta, add acid to water. Because if you add a small amount of acid, concentrated acid to water, it's exothermic, but you've got a large volume of water to absorb that heat. But if you add water to concentrated acid, that water is going to heat up so fast it will vaporize and splatter in your face. So you do that with acids and with concentrated bases, because they're always, when you make solutions with them, they're always exothermic, extremely exothermic. And concentrated sulfuric acid is 98%. So it's got very little water to start with. Let's see. And the freezing of water is exothermic. Right? You've got to give up heat to go from a liquid to a solid. So A is the best answer. Y'all get this in high school? Does this look familiar?
Some.
Oh, okay, okay. I was thinking about you memorize the periodic table. Okay, that's fine. Let's see, what am I on? 4. Which statement about hydrogen bonding is true? Well, we know what hydrogen bonding is. We have some part of the molecule here, and it's attached to an oxygen and a hydrogen, or it could be attached to a fluorine. Well, that won't work because fluorine can only have one bond. So it would have to be, this would have to be the hydrogen, right? Or it could be sulfur, like that, to some other part of the molecule. And you get a dipole here, a very strong dipole. And then each of your neighbors can come in there, and this, you can form a bond between this one and the hydrogen of the next one, or this one and the hydrogen of the next one. So let's look at our statements, which are true. All those are unique statements, so all we have to do is find the right one. A says hydrogen bonding is the intermolecular attraction forces between two hydrogen atoms. No, sorry, because they're both going to be positive, slightly positive. So A doesn't work. Hydrogen bonding capabilities of water molecules cause that's butane, to be more soluble in water than CH3OH. That's also false, because methanol has the hydrogen bonding capability here, whereas butane doesn't. Right? Look for those electronegative atoms in the molecule. Nitrogen, oxygen, fluorine. Attached to a hydrogen. Then you can think possibly hydrogen bonding. So B is false. C says hydrogen bonding of solvent molecules with a solute will not affect the solubility of the solute. Beg to disagree. Hydrogen bonding is a very, very effective force applied to solubilizing a compound. Yeah. Like dissolves like. Okay. Hydrogen bonding interactions between molecules are stronger than the covalent bonds within the molecule. What's wrong with that statement? If the intermolecular forces are stronger than the intramolecular forces, your molecules will be ripped apart. It's just that simple. So the intermolecular forces must be weaker than intramolecular. And then E, by process of elimination, E is probably the answer. Hydrogen bonding arises from the dipole moment created by the unequal sharing of electrons within certain covalent bonds within a molecule. That's a little too general, but it works. Compared to the others, E is the best answer. About 5. Which of the following favors the solubility of an ionic solid in a liquid solvent? Well, I would say if you're going to solubilize an ionic solid, you need a polar solvent, definitely. And let's see, a large magnitude of the solvation energy of the ions. All right, we didn't talk about that in any detail. What is the solvation energy? The solvation energy is what takes some compound and puts it in solution. All right, so there's going to be some energy here that is well, if we go back to our three-step process, remember that one, right? The first step is break the bonds. And the second step is for the solvent. Two is make a hole. So those are endothermic processes. Delta H has to be positive here and positive here. And the solvation energy is the energy you get back in this step, where you get the solute solvent interaction form. Solvent interaction form. And this is exothermic. Okay. So does that answer the question though? Which of the following favors the solubility of an ionic solid in a liquid solvent? A large magnitude of solvation energy. Yeah. If there's a strong attraction between the solute and the solvent, that's going to favor solubility, sure. Regardless of how much energy it takes to break them apart, this is going to favor solution. Yeah, so A is true. B, a small magnitude of the lattice energy of the solute. So lattice energy is, by definition, we haven't talked about that yet, have we? Lattice energy. Okay, lattice energy is defined as you have ions in gas phase, the anions and the cations in gas phase, and they come together to make the solid. Okay? And the amount of energy that's released in that process, this is always exothermic. But we have to start from the gas phase so that we don't introduce any phase changes. This is a deposition process. We go from these gas ions to this solid, and we get a lot of energy back. So if a small magnitude of the lattice energy, would it favor solution? Well, yeah. If it's a smaller value here, it takes less energy to go back that way and make our ions, right? Break the bonds. See what that means? Okay. Takes less energy to break the bonds. Then now these are available for the solvation process. So B is also true. Large polarity of the solvent. Well, for an ionic solid, yeah, large polarity helps a lot. You know, maybe that's why they call water the universal solvent, because it dissolves so many things, and so many things are ionic in nature. Okay. Well, all of the above are true, right? A, B, and C are all true. I don't know if we have time to do 6. Let me hold 6 out. Easy 6, because it's going to take some time to do that one. And let's see if we can get through the rest of them first. Yeah. I worked through 6 in the worked problems, right? So if we completely run out of time, then the explanation is there. Use the following drawing of a gaseous solute in equilibrium with a solution to help answer the question below. Okay, now we're talking about Henry's law. Remember? Henry's law. So the concentration of a gaseous solute is proportional to the pressure times some constant. And so the greater the pressure, the higher the concentration of the gaseous solute in your solution. Okay, now let's go back to the question. Which of these following statements is true if the piston is pushed downward? We're increasing the pressure by decreasing the volume. That's Boyle's law. So A says this will cause the pressure of the gas to increase and the concentration of the dissolved gas to go down. It's the opposite. Right? A is false. B says this will cause the pressure of the gas to decrease. No, we can stop right there. Pressure is going up. Otherwise, Boyle rolls over in his grave. This will cause the pressure of the gas to increase and the concentration of the dissolved gas to go up. C is true. What about the others? Cause the volume of the gas to decrease and the concentration of the dissolved gas to go down. That's false. Right. And then E says this will cause the volume of the gas to increase. No. Okay, so we found our answer. C is the best answer. It obeys Hooke's law, or Henry's law. Excuse me. I'm getting physics confused with chemistry. Well, actually, this is a physical process. Anybody know what Hooke's law is? No, you haven't had physics? Okay. It describes the way a spring behaves. If you double the mass suspended from a spring, you'll double the length. Really simple. But it's easy to get confused. They both start with H. Number 8. Which of the following correctly states the relationship between temperature and the solubility of a substance in water? All right. It doesn't say what substance is. Is it a gas? Is it a liquid? Is it a solid? But it does tell us what the solid is, water. Okay, so A, B, C, D, and E. Do we have any wonky ones in there? Yeah. A and D are correct. A and D, correct. Okay. So we have to look at A, B, C, and D. We're looking for the correct statement. So we have to look at all of them to be sure that D, or maybe A and B, or A and D, excuse me, or maybe one of the others, B or C. So A says the solubility of a substance in water increases as the temperature rises, especially for gases. That's the kicker right there. Solubility of gases in water decreases with the increased temperature. Right, so A is false. You have to read the whole statement to be sure. B says the solubility of a substance in water decreases as the temperature rises, especially for ionic solids. Well, it only happens for some ionic solids. Most ionic solids become more soluble as we increase the temperature, and the solubility decreases as the temperature rises for those other solids. Right? So B is not true for all solids, ionic solids. C says the solubility of a substance in water with temperature, in water with temperature cannot be accurately predicted, especially for ionic solids. Now that's true. We can say most ionic solids become more soluble with increasing temperature, but some become more soluble with decreasing temperature. Right. So C is a good statement. And since C is true, then E can't be true, and there's no place for D either. D just says the solubility of a substance in water decreases as the temperature lowers, especially for gases. Solubility decreases as the temperature. Well, as a blanket statement, that's false. But the solubility of gases increases as the temperature decreases. So D is also false. We found our answer. All right. You'll notice that most of my questions are multiple choice. That's so I can grade them quick and give them to you before you leave the class. There will be occasions for short answers or drawing stuff, but most of the questions are multiple choice. A solution contains 1 mole of liquid A and 3 moles of liquid B. Okay, so we've got 1 mole of A and 3 mole of B in solution. This solution has a vapor pressure of 314 torr at 25 degrees, and it looks like the temperature is not changing. So this solution has a vapor pressure of 314 torr. Cool. Okay. That's for the solution. At 25 degrees, liquid A has a vapor pressure of 265. So the pure vapor pressure for A is equal to 265 torr. 265 torr. Okay. And we're probably going to get the pure for B is 355 torr. So pure for B equals 355. Okay. What do we know about this, where the concentration of B increases this way and the concentration of A increases that way? So if it increases this way, then 100% A would be up here at 265. And it would go down to 0 there. As B increases, 100% B is 355. It'd be up here somewhere. That. Okay. So as the composition changes, the ideal would be between these 2 points right here. Okay. But is that the case? Now, how do we calculate what would be the ideal pressure based upon these 2? Well, they follow mole fraction law. What is the mole fraction of A in the total? It's 25%, isn't it? Right, 1 out of 4. So if we multiply this times 0.25, we get a contribution to the total. 265 by 0.25. I get 66.25 torr. And the contribution of B would be 3/4 or 0.75 times 355. And that would be 266.25. So the ideal would be, let's see, it would be somewhere over here, right? About in this place. So we were looking at that position right there. So we would add this one together with that one to get this one. Okay, so what would that be? Add those together. We can round it off to the nearest. 333 torr would be ideal. Okay. All right. The question is, which of the following is true? The solution exhibits a positive deviation, a negative deviation, or ideal? Well, it's not ideal, right? It's not ideal because it's not the same as the measured value for that mixture. So it's a positive deviation. Excuse me, it's a negative deviation. It's going like this. So this value is 314 rather than 333. It's a negative deviation. Sorry. Okay. All right, 12. A cucumber is placed in a concentrated salt solution. What will most likely happen? If the solution is concentrated in, say, sodium chloride, would be a good choice. Concentrated. It's very high concentration of sodium chloride. How does that compare to the cucumber? Sliced cucumber. Well, you've got individual cells, right? And each cell has a membrane on it that we can model as semi-permeable. That is, only water will pass through, or gases, but gases don't enter in here. Well, which one is this solution? Hypertonic, hypotonic, or isotonic? Right? If it's isotonic, this concentration is the same as inside the cell, inside the cucumber, and nothing happens. If it's hypotonic, we got more water out here than we do inside the cell. So the water moves in and the cucumber swells. If this is hypertonic, then we've got less water out here than we do in the cucumber cells, and water moves out. Okay, so probably it's this one with a concentrated sodium chloride solution. So we should expect water to move out of the cucumber. So where does that fit with our answers? Water will flow from the cucumber to the solution. Yep, that's it. And that was A. Okay. Y'all get this in biology? Everybody taking biology? Yeah, they talk about this in biology. Okay. 13. Osmotic pressure depends on all but which of the following? For that, we probably need the formula. What's the formula for osmotic pressure? Looking for pi. Where's pi? Is it not in here? Ooh. Did I leave it out? On my copy. Did I put it in your copy? Because this may be an old one. Useful information. High osmotic pressure. I don't see it. Well, let's see if I can remember what the formula is. Osmotic pressure is proportional to the molarity of the solution, the gas constant, and temperature, correct? Do I remember that correctly? I think so. And then also, if we have some change in the solute when it goes into solution, either ion pairing or splitting apart, we have the Van Hoff correction. That's a possibility too. Okay, the question depends on all the following, on all but which of the following. So which is not included in this expression? Well, pressure, that's not included. Right? Pressure is nowhere to be found. So pressure is excluded. Doesn't matter what the pressure, the atmospheric pressure is. The rest are there. Molarity, temperature, ratio of moles of solute solution volume. Well, that's another way of saying molarity. Okay? It's easy. How about 14? Definition time. All right, shaving cream is the example of which colloid type? It's a foam, right? A foam, a gas and a liquid. What's another type of foam? Actually, it's got a prefix. Solid foam. You know the tiles on the space shuttle and the tiles, the ceramic tiles they use on most re-entry vehicles for spacecraft now. Those are solid foams. They're basically glass or silicate matrix with gas trapped in there. And that makes them very low heat transfer. Right? So what happens? Well, as you hit the upper atmosphere and you start building up heat from friction, those things start to glow, but they don't transfer their heat into the vehicle. In other words, the heat that's generated by that friction is transferred to the air, and it flows off and takes the heat away. But these ceramic materials are very brittle, so they don't like impacts of any kind, like birds or pieces of foam off of your fuel tank. Like, actually, that wasn't ceramic tile, that the space shuttle where the wing got a hole knocked in it. That was which one was that? Columbia? Challenger was the first one, right? It blew up on takeoff. And I think Columbia, when it came back, they didn't realize they'd had a hole knocked in their wing, and the spacecraft came apart. So we lost another crew. That was carbon-carbon. That's a different type of composite in the surface of the wing. It stands higher temperatures than either the ceramic bricks. But it doesn't like strikes of any kind. So when it took off, a piece of foam came off of that big orange tank that sat outside the space shuttle. And that foam, you think, piece of foam? That didn't weigh anything. Yeah, but you're going like 3 miles a second. And when it comes off of there, it smacked the edge of that wing and knocked a hole in it. They could see it on the video. Once they started looking for causes, they could see it. They didn't see it during takeoff. Okay, let's see. So that's a foam. What's an aerosol? An aerosol is the gas is the suspending medium. Now we're talking about what? We're talking about, I just went blank. Not solutions, but colloids. Colloids. An aerosol is fine liquids. Okay, that's a notification. Fine liquids or solids suspended in a gas. Right? So smog is an aerosol. Clouds are aerosols. Emulsion, that's a liquid in a liquid. That's homogenized milk. Sol is a solid in a liquid, I believe. Solid in a liquid. That's like Jello. And coagulate is not a colloid type. Oh, there it is. All I have to do is read it. You guys, you need to catch me on these things. Right? When I can't remember a word, if it's right there on the screen, just holler. Coagulate is related to colloids, but it's not a type of colloid. Coagulation is what happens when the colloid is destroyed, when the suspended particles drop out of suspension. And that can happen with a different number of ways. One is heat. Other is acid or some ion. You know, when water treatment, when they take water from the lake, which lake is it? I forget the name. Beckley gets its water from a lake. They dam up Glade Creek, and we've got a lake up there. I've driven by it before. You have to treat the water before you can pump it through the city pipes. Right? So one of the first things they do is they remove suspended solids, and they add ions like calcium ions or aluminum ions, and they attract these particles to themselves, and they get so heavy that they just drop out. They coagulate. So when they add those, then they send them through this snake-like traverse where the water goes back and forth, and it moves slowly. So you pump it in there, it's at a fairly high velocity, but as it goes into that large volume, it slows down. And then by the time it gets out the other end, all that coagulant has dropped out. And then as an additional filter, they run it through a sand bed. And that takes out a lot of the other particles. Then they test it and usually add chlorine. Sometimes a lot of chlorine. So when it gets to your house, it's safe to drink, but it may not taste very good. So that's where we run it through a carbon filter. Most refrigerators have them built in now. It's a combination of activated charcoal and minerals, because distilled water doesn't have a taste. Doesn't have a good taste either. Also, it's corrosive, right? If you try to drink distilled water day in and day out, it'll eat the enamel off your teeth. So you want some electrolytes in the water to balance out. Now, there's a big debate going on now about fluoridating water. Is it necessary? The original reason for fluoridating your water was primarily for interior parts of the country where you don't get fluorine in the water naturally. People that live on the coast, they eat seafood and they get water that's seafood and water that's naturally fluoridated. So it prevents goiter. Your thyroid gland get big because it's deficient in fluorine. But they do put fluorine in your water, and they put it in salt, right? No, iodine in salt, excuse me. That's goiter. Iodine's goiters. Sorry. Fluorine's for your teeth. I'm getting two things mixed up. Iodine's for your thyroid gland. Fluorine is for your teeth, because they were afraid that young children, when their teeth are developing, they might be getting calcium in their diet from milk products, but they're not getting fluorine. And the enamel in your teeth is a complex mineral that has fluorine in it. Let me just put it that way. But there's some question now as to whether fluorine is necessary and whether the benefits outweigh the risks, because there are some risks in fluoridating your water. And it's not the same as the John Birch Society used to say, that it's communist plot. Okay, we're in the moderates now, 3. Yeah, I'm using every time. Moderates. Hopefully it won't take long for just the introduction in the lab. A 0.2 molar solution of solute X in benzene. So the concentration is 0.2 molar solution of X in benzene. Okay, that's given. Displays an osmotic pressure given by the formula 0.1 molarity or T, right? Oh no, that's combined. We leave the molarity out. So this is a combination of I times molarity. Okay, the way it's written. So what's going on here? If the concentration is 0.2, we make up a solution that's 0.2 molar in X. Then why is this 0.1? Well, that means this I has to be 0.5. 0.5 times 0.2 is 0.1. right? Is that right? Let me do that. Let me do the calculation. IM equals 0.1. If this is 0.2, then I equals, 0.1 divided by 0.2. So I is 0.5. That's right. So what does that mean? Well, that means you've got fewer particles in solution than you think you do by half, right? You've got maybe ion pairing, maybe some other type of pairing. So X exists in benzene not as X, but as two X's. That decreases your concentration from 0.2 to 0.1. 0.1 will give you the same number of moles of X as 0.2 of the individual X's. Okay, that's what we're saying. So B is the best answer. X exists in benzene as X2. All right. If there are no objections, we'll move on to the next one. Number 4. Let's see. Do I want to deal with 4? Yeah, we can do 4. In the amount of time available. Which of the solutions? 0.1 molal sodium chloride, 0.15 molal glucose, and 0.1 molar calcium chloride would have highest vapor pressure, lowest boiling point. So we've got 0.1 molal sodium chloride. Oops. What that is. 0.5 glucose, 1.5 molal glucose, and 0.1 calcium chloride. Okay. So we're looking at vapor pressure and boiling point. So this is vapor pressure, and this is boiling point. Okay. And we want for vapor pressure, the highest vapor pressure. And for boiling point, the lowest boiling point. Okay. So what I've done is extract everything out of that word problem, put it up here so it makes sense. All right. So what would we expect? For well, either one. These are colligative properties that we're looking at, vapor pressure and boiling point. So it doesn't matter what this is intrinsically, sodium chloride, salt, glucose, calcium chloride, doesn't matter. What matters is the concentration. So what's the concentration here? Well, we're actually looking at 0.2 molal because you can split these into two ions, right? This one doesn't dissociate. So its concentration is same as given. This one splits into 3. So this one's 0.3 molal. Okay. So vapor pressure will go down as you increase the concentration. Right? So the lowest is going to be 0.3. The next lowest is 0.2, and the highest is glucose. So the highest vapor pressure will be glucose. Right? How about the lowest boiling point? So we increase the boiling point by increasing the concentration. So the highest concentration is going to be the highest boiling point. Right? And the lowest boiling point is going to be the lowest concentration, because we increase the boiling point by increasing concentration. So the lowest is going to also be glucose. So which one is both glucose? D. Yeah, D. The reason I went to all that trouble to say which is the highest and which is the lowest is maybe I take that same question and just change the conditions. Right? Okay. So you understand why it's this one, so that if I change something, you'll know how to solve it. 5. Oh, we're working with okay, 5. Now what are we looking for? Lowest vapor pressure, lowest boiling point. Well, we found the lowest boiling point already. Lowest vapor pressure is going to be the highest concentration. So that's calcium chloride and glucose, which is C. All right. Difficult? 2. You know, it's a good thing I held this one out because 6 is not easy. It should be with the difficulties, I think. Okay, let's go ahead and look at number 2 then. A solution is prepared from 53.8 grams of a non-volatile, non-dissociating solute and 85 grams of water. Okay. The vapor pressure of the solution is 60 at 60 degrees is 132 torr. The vapor pressure of the water at 60 degrees is 150 torr. What's the molar mass of the solute? Okay. Go back to first principles. What is molar mass? I abbreviate that molecular weight. It's the mass per mole. So in other words, from this problem, we have to extract both of these values, mass and moles. So the solution is prepared from 53.8 grams of the solute. And we want to know the molar mass of the solute. So we've got the mass, 53.8 grams. What we need is the moles of the solute. Okay, so the conditions given, 53.8 grams, dissociating solute, and 85 grams of water is the mass of the water, of the solvent. So the mass of the solvent equals 85 grams. Okay. The vapor pressure of solution at 60 degrees of the solution is at 60 degrees is 132 torr. So the vapor pressure of the solution is 132 torr. And at the same temperature, the vapor pressure of water is 150 torr. The solvent equals 150 torr, right? 150 torr, yeah. So from this, we need to find out how many moles that is. All right. What do we know about vapor pressure? The vapor pressure of the solution is equal to the mole fraction of the solvent times the pure vapor pressure of the solvent. Okay. Rail law. Let me see if I got that right. Measured vapor pressure, we know the solvent's pure times its mole fraction, then we can find that one. Okay, so what is the mole fraction of the solvent? The mole fraction is the moles of solvent per total moles. And the total moles would be the moles of the solute plus the moles of the solvent. Okay, that's the total. This is what we need right here. Okay, so if we've got 85 grams of water, how many moles do we have? Can we figure out the number of moles of water? Yeah, Molar mass is all you need. Let's see, grams on the bottom, moles on the top. 18.02 divided into 85. I get 4.717 moles of water. Okay. So this expression here, if we substitute this in here, what we've got is 4.717 moles of water over moles of solute plus 4.717 moles of water. Okay, that's that. And we know the vapor pressure of the pure solvent is 150, correct? 150 torr. And that's equal to 132 torr. Right? So now we have an equation in one unknown here. We can solve for it. Okay, so what do we got? Well, let's see. We can multiply this one times that one, right? 150 times that. And that gives us 707.55 is this combination here. So let me pull that over here. 132, I'm going to leave the units out because I don't have room. And we've got 707.55 in the numerator. And we have N, I'm just going to leave this in, plus 4.717 here. Right? Did I miss anything? So now we need to bring this over here. That gives us 132 N times 132 times 4.717, which is, let's see, not equal, plus 622.64 equals 707.55. Now we move this one back over here by subtraction. Subtract that from this one. Yep, that button. This is 84.90. And N then would be this one divided by that one. Which would be 0.64 moles. So now we can put 0.643 moles here and divide that into 53.8. And I get 83.6 grams per mole. That even close? Yeah. E. Okay. No, it was a lot of work. But we start with this proposition, and then we look for the information. We found this immediately. This one we had to work for, that number of moles. And we had to use, with the information given, the approach that works for the number of moles is vapor pressure calculations with Rayleigh law. Okay. I think I put that one in the difficult range because it was so involved. Very complex. It's a complicated calculation. The reasoning really is not that complicated. And that's very often the case. Sometimes you have to take a complex problem and break it apart into pieces and then pull the pieces back together to solve it. I'm starting to lose this one. You have 10.4 gram mixture of table sugar and table salt. When the mixture is dissolved in 150 grams of water, the freezing point found to be minus 2.24 degrees. Calculate the percent by mass of sugar. Okay, this one's involved also. So let's hold that one because I'm already Yeah, I'm already into your lab time, and I don't want to eat it all up. This one is well characterized in the handwritten document. It requires algebra, and put it that way. So easy 6, chapter 11, 6. Solid potassium fluoride has a lattice energy of minus 804 kilojoules per mole and a heat of solution in water of minus 15 kilojoules per mole. Where rubidium fluoride, so that's potassium fluoride versus rubidium, which is the next largest alkali metal, rubidium fluoride, has a lattice energy of minus 768 kilojoules per mole and a heat of solution in water of minus 24 kilojoules per mole. Which salt forms stronger attraction with water? Okay, so what we need to do is, before I pull those numbers out, go look at the theoretical setup we've got going here. Excuse me. So remember when we were calculating the heat of solution, it's the summation of these three heats that we discussed in the lecture and earlier in a previous problem. This is the heat required to break solute bond. This is the heat required to break solvent bond, make a hole. And this is the formation of solute solvent bond. Okay. So the question here, let's work it backwards. Which salt forms stronger attraction with water? Which one would be the term that gives you attraction to water? If water is the solvent, the stronger attraction would be located here, wouldn't it? Which one is the stronger value here? Now, what do we mean by stronger? In quantitative terms, stronger is the more negative because it's an exothermic process. When these things come together, they're going to give up energy. And the more energy they give up, the more stable they are. That's the stronger attraction. So we're looking for the most negative value here. Okay. Okay. So what are we given? Lattice energy. What's the lattice energy? Well, the lattice energy is, well, just that definition I gave you before, where you have the X and Y as a gas. Let's see, this is negative. Sorry. And it could be 2 pluses or 3 pluses. It doesn't matter for argument's sake. And this yields the XY solid. And this value is going to be exothermic. I feel myself going off the rail already, so don't mind. I'm going to pull this up, keep myself on track as I try to explain it. All right. So already I've made a mistake. Let's put the values that we've got up here so far. All right, for KF, what are we given? We're given minus 804 kilojoules per mole is the heat of solution. Right? And I don't see that up there anywhere. So the heat of solution is going to be a combination of those. Actually, I do see it up there. Okay. heat of solution is minus 804 kilojoules, kilojoules per mole. And then rubidium fluoride, the heat of solution is 768. Right? No. No, that's the lattice energy. The heat of solution is minus 15 kilojoules per mole. And this is minus 24. There we go. So, now the lattice energy, let's go ahead and put that up here. Lattice. This one is the minus 804. And this one, lattice, equals minus 768. 768. Well, okay. All right, so this is what the lattice energy represents. Okay, when we bring these two together. Step back, right. When we break these bonds, that's actually the reverse of the lattice energy. Right? Remember when I was talking about that? The amount of energy you put in to break the bonds would be this. Okay. So this would be negative lattice. That's what goes right here. Negative lattice. Where you break the solvent bonds and form the solutions, this is together the heat of solution. Okay. So here's the heat of solution. That's what this term represents here. All right. One thing that's common to both of them is breaking solvent bonds, the bonds of the water, right? So the difference between the two, which is what we're looking for, we're trying to find which one has the strongest attraction for water. These two together give you the heat of solution of each one, but this is the same for both of them. This is where the difference is. Okay. All right. So the heat of solution of each one would go in this term right here. And the lattice energy would be a negative value for that one, would go here. And then this would be our unknown. Okay. And then we compare that value to see which one is more negative. Okay. So if we do each one separately, so for KF, we would have the heat of solution, which is minus 15, and they're all kilojoules per mole. So I'm going to leave the units off. So save space. And then this one is negative lattice energy, 804. And this is plus heat of solution. Wait a minute. That's not right. That's not heat of solution. Is it? No. That's heat of hydration. Because the whole thing is heat of solution, right? You guys are supposed to keep track of this and correct me when I'm wrong. Okay. So this term right here is the one that tells us the affinity of each one of these for water, that heat of hydration. Got quiet all of a sudden. So this is delta H hydration. Okay. On this side, we would have minus 24 equals a minus, this is a minus here, a minus 768, a plus there. So now we can solve for each one and compare the values. right? All right, so this would be, that'll be a positive. When it comes over here, it's a negative again. All right, so 15 and 804 would give us a negative 819 equals the heat of hydration 4 kF. And this one would be 768. Oh, excuse me. Yeah, that's right. Positive here, negative there. Positive here, negative there. 768.24 is minus 792 equals the heat of hydration for rubidium. Okay, so which is more negative? That one. So KF has a stronger affinity for water than does rubidium fluoride. Not much difference, but there's measurable difference. Now let's see, does that agree with what? Yeah. Oh, it's a multiple choice. So KF, since it has a more negative heat of hydration, that's C. All right. And we'll look at number 4 in the difficult section. I know why I haven't moved this one into difficult, even though it is difficult. It's because I've already handwritten the description. And if I move it, I've got to change that document again. And my knuckles won't stand the damage. Okay, so difficult 4. Let's go down to that one. That's moderate. Here we go. Difficult 4. Here we go. Okay. I'll keep myself on track. Okay. This is 4. All right. So now for this one, we can put what we know up on the board first, I think. We're calculating the percent by mass of sugar in the original mixture. So we've got a mixture of sugar and table sugar or sucrose and sodium chloride. So that mass, the total mass, is equal to 10.4 grams, right? 40. Never throw away a decimal. When the mixture is dissolved in 150 grams of water, so the mass of the water, which is the solvent, is 150 grams. So how many kilograms is that? I know we're going to need that, so we might as well do it. 0.150 kilograms. Right? Because we're talking about freezing point depression. That's a colligative property. And the freezing point now is found to be minus 2.24 degrees. So what's the change in temperature for the freezing point? It's 2.24 degrees. It's below zero, that much. 2.24 degrees C. And this is going to be the absolute value because of the way the formula is set up. What is the formula? Equals whatever the constant happens to be for water, the freezing point constant for water, times, and we're going to have a Van Hoff correction, right? Sucrose doesn't dissociate, but sodium chloride does. Okay, that's going to be one of the kickers. And then times molality. Okay. The problem is this is not a pure substance that we're putting in there as a solute. It's a mixture. This is equal to the mass of sodium chloride plus the mass. I better spell it out. because that means molality. And this is sucrose. Okay. All right. So if we're looking for percent, which one? Sugar. Percent by mass of sucrose. That's what we're after. Well, if we let X be the mass of sucrose, we already have the total mass. So we really only need to know the mass of the sucrose to answer the question. So if we let X equal mass of sucrose, then what would be the mass of sodium chloride? It would be 10.4 minus X, right? Okay. All right. So I probably should have written that over here. Let's put it over here so I have some more room. 150 grams equals 0.150 kilograms. Okay. And absolute change in temperature for freezing point is 2.24 degrees C. All right. Okay. We need to know in some form or fashion, this is going to be including an unknown. We need to know how to calculate the molality for the solution. Well, as it turns out, the I for sucrose equals 1, and the I for sodium chloride equals 2. So here's the assumption that we have to make. We have to make the assumption that this formula can be parsed into an additive, a linear addition of the two functions. So what we're saying is this change in temperature is due to the I of sucrose times the K for water times the molality of sucrose plus the I for sodium chloride times the K for water times the molality of sodium chloride. Okay. That's the first trick that you need. Aside from the algebra, of course. Now, let's see. Be sure I'm on track. Okay. So if I bring that formula over here, what is the expression of the molality of sucrose? Well, we need to know the moles, right? So we're given the formula, but we're not given them the molar mass of sucrose. So we have to calculate that, right? C12H22O11. That's sucrose. So sucrose is going to be C12, so 12 times 12.01 grams per mole, 22 hydrogens, yeah, 22 times 1.01 grams per mole, and then 11 oxygens, 11 times 16. So this is going to give us the molar mass of sucrose because we've got to calculate the molality somehow. Let's see, 12.01 times 12 is 144.12, and then 1.01 times 22 is 222.2, and add those together, and then 16 times 11. And let's see, did I do that right? I better do that again. Okay. 1.1. 2. 15, turn 11 times, and then add those together. There we go. That's looked better. 342.34 grams per mole. Okay. And sodium chloride is a little simpler. It's just one sodium at 23, and chlorine is 3545. So that's 58.45 grams per mole. Okay. How do you calculate the molality of each one for these values here? Well, the molality of sucrose is going to be first the number of moles. So we have to divide the mass X divided by 342.34 grams per mole, right? Then grams cancel and leaves us with moles. But the molality is that per kilogram of solvent per 0.15 kilogram. So that's the expression for molality for sucrose. How about the expression for molality for sodium chloride? Well, in this case, we have 10.4, right? Minus X. And that's divided by 58.45 grams per mole. See, I usually string them out in dimensional analysis, string them out like this. But if I string that out, that means this 58.45 goes in the bottom and the moles goes in the top anyway. And then this is relative to 0.150 kilograms of salt. Right? So now we need to know the K for water. Uh-oh. It's not there. Is it in useful information? Freezing point, depression constant. No, specific heat. Heat of fusion, vaporization. There it is at the bottom. KF for water. 1.86 degrees C per mole out. So this K, stick it up here. K freezing point for water is 1.86 degrees C per mole out. The other way to write that is 1.86 degrees C times kilogram per mole. If you put molal in the denominator, that's like flipping moles per kilogram. So either way works. Okay, now we've got all these pieces. We can put them together over here. So the where's my temperature? Here it is. 2.24 degrees is the freezing point depression. 2.24 degrees C is equal to, what's this one for sucrose? That's 1 times the K, 1.86. I'm going to try to save room. Just put 1.86 in there. And then the expression for molality for sucrose. If this is in the divisor, this is in the denominator. Let me see. I want to get that right. Oh, okay. I'll make it a little more complicated than it needs to be. I'm going to do it the simplified way. Hold on to that thought. The molality is the number of moles of sucrose per 0.15 kilograms. And then we add 2 for the sodium chloride, and it also has 1.86 times the moles of sodium chloride per 0.15. And what I did in there that I was starting to not do here was I factored out things that were common. So you can factor out 1.86 and 0.15 out here on the outside. So 2.24 then equals factoring out the 1.86 divided by 0.150, right? Numerator, denominator. This is common both expressions, so we can factor them out. And now all we have left in here is moles. Actually, all we have left on this side is moles of sucrose. And plus 2 times moles of sodium chloride. Right? Did I do that right? Everybody, algebra masters here. So if I resolve this and then divide it over here, I get a value over here plus these two by themselves. So that's what I'm going to do next. I'm going to divide 1.86 by 0.15, and then that number, 1.24, I'm going to bring it over here. And that's 0.180 equals moles of sucrose plus 2 times, looks like nitrogen, moles of sodium chloride. Okay. Trying to call me. Jump made it. Jump phone call. Okay. Now that we're up to this point, now we say, how do we calculate the moles? So here's what I'm going to do. Instead of molarity here, I'm going to change that to moles. This is moles of sucrose, right? Mass divided by molar mass. That's moles of sucrose. And this one, I'm going to make moles of sodium chloride. And that means I can get rid of this part. There, that's much more better. So for this one, I can substitute X divided by 342.34. And this one, I can put 2 times 10.4 minus X divided by 58.45. There we go. This is 0.186. All right, so how do we resolve this one? Well, first thing I do is divide 2 by this, and then multiply it by that and by that. And in the interest of time, let's see. Yeah, I guess I better do it. But I might have to erase something and put it somewhere else. Let's say I put it, well, I can do one step down here, and then I might have to move over there. Okay, so we've still got 1806, right? Equals X over 342.34 plus, and now 2 divided by 58.45 is 0.0342. And I'm going to take that and multiply it by this and by that. So we've got this X, we've got a minus. That minus X is 0.034. to 2x. That's this divided into that times that. And then this divided into that times this will be 10.4. And this is plus 0.3559. There we go. Now we need to get all our unknowns on one side and all our knowns on the other side. So this would have to come over here. Let's see. Yeah. So I'm going to say this one subtracted from that one, which I happen to have right here, and all I have to do is hit minus. So this is minus 0.1752 equals. So now what do I have left on this side? I have these right here. So this is 1 divided by 342.34. Inverse. So I'll take the inverse of that. Then I subtract 0.03422. And that gives me a minus 0.0, say 1, 2, 3, 1, 2, x. So I'm going to say x is this, divide both sides by that value. That gives you a positive value. So that's 5.60, rounded off, grams is the mass of sucrose. Okay. Now, percent by mass is just 5.60 divided by the total, 10.40 times 100. And rounded off 0.5, excuse me. Multiplied by 100. So this is 53.8%. Close enough, 53.9. Okay, I know that was a lot of trouble and too much algebra for most people. So let's see. Long story short, that looks like an extra credit problem.